What are capacitors? A capacitor is a device that stores electric charge. This enables it to store energy in the form of potential energy. While it sounds similar to a battery, they are not the same thing. Inside the battery, a chemical reaction is taking place, with electrons flowing in and out. In contrast, a capacitor is a passive device. Analogy: similar to a bank vault for electrons, it is appropriate for use in oscillating circuits like in radio with waves coming. The upper plate will be charged by a battery. If it charges at up to plus Q, the bottom plate will be negatively charged with negative Q due to induction. Side view: an electric field exists between the plates of a charged capacitor. What happens if the capacitor's battery connection is compromised? There will be nowhere for the charges to go. There will be leakage through air, but very little. The energy of the electric field will be stored. Circuit 1. The battery will provide charge to the capacitor when the switch S is closed. 2. The discharged electrons of the battery will start to flow out and start charging the capacitor's plate B. These electrons will continue to flow until the capacitor is fully charged, that is, the vault is full. Number 3. Plate B will be electrically negative. Number 4. Even though a capacitor has an open path, current will still flow through the circuit until it is charged. Since A will be positively charged, any electrons that collect on B will be repelled by electrons on A. As a result of attraction, these repelled electrons will return to the positive terminal and maintaining the circuit's continuity. B changes to negative Q after a lengthy delay, while A charges to positive Q. The capacitance, C, determines how many coulombs of charge can be stored. In the given circuit, Vc represents the voltage across the capacitor. Once fully charged, the voltage across the capacitor will be exactly V volts. In the second circuit, this comprises of a parallel connection which we'll study later. The voltage across each capacitor will be exactly V volts. Also, V of C1 is equals to V of C2, which equals to V of C3, which is equals to V volts. When switch S is closed, a massive current flows through the circuit as the capacitor accepts more and more charge. However, as the capacitor's storage becomes full, less current will flow because it will accept fewer electrons. Charge on a capacitor is given by Q is equals to the product of capacitance times voltage. Unit of capacitance is farad in SI system. 1 farad will be equal to 1 coulomb divided by 1 volt. The capacitance of a capacitor with a charge of 1 coulomb and an applied voltage of 1 volt across its plate is defined as 1 farad. Calculating capacitance. Q equals CV, which implies C is equals to the ratio of charge to voltage. Step number 1. Assume a charge Q exists on the capacitance plate. Step number 2. Calculate the electric field between the plates using Gauss's law and then use it to obtain the enclosed charge Q enclosed. Q enclosed is given by epsilon naught times the closed integral of E vector dotted with the area vector dA. Step number 3. Using electric field, calculate the voltage V across the plates. The change in voltage, or the potential difference, V final minus V initial, is equals to negative times the integral with limits going from initial to final of E vector dot ds vector. Step number 4. Finally, obtain the value of C. Parallel plate capacitor. The electric field between two large parallel plate capacitors can be calculated by using electric field is equals to sigma over epsilon naught, equation number 1, where sigma is the surface charge density and epsilon naught is the permittivity of free space, and sigma is equals to charge per unit area, equation number 2. Now from Gauss's law, epsilon naught times the closed integral of electric field dotted with the area vector is equals to charge enclosed, equation number 3. Ignore the fringing field at the edges and we calculate the enclosed charge within the Gaussian surface as shown in figure to get epsilon naught times the closed integral of E vector dotted with the area vector is equals to positive Q, equation number 4. Inside the Gaussian surface, Q is positive. Considering only the field lines parallel to the area vector, we get epsilon naught times the closed integral of E times dA times cosine of 0 degree is equals to positive Q, equation number 5. Assuming the electric field to be constant, sigma and epsilon naught are fixed, we have epsilon naught times E times A is equals to positive Q, equation number 6. Now, the difference in voltage between the two plates can be expressed in terms of the work done on a positive chest charge Q as it moves from the positive to the negative plate. V is equals to negative times the integral 0 to d E vector dot dl vector, which will be equals to negative integral 0 to d E dl cosine of 0 degree, which is equals to negative E times integral 0 to d dl, and that finally gives us negative E times d, equation number 7. Following from the definition of capacitance, the absolute value of capacitance is equals to the absolute value of charge divided by the absolute value of voltage, and using equations 6 and 7 we have C is equals to epsilon naught times E times A divided by E times D. The E and E from the numerator and denominator gets factored out, leaving behind C equals to epsilon naught times A over D. This is the capacitance of a parallel plate capacitor. Cylindrical capacitor. By calculating the voltage differential between the conductors for a specific charge on each, the capacitance for cylindrical capacitors can be determined. The electric field outside a charged cylinder is found to be E equals lambda over 2 pi epsilon naught times R. When Gauss's law is applied to an infinite cylinder in vacuum, integrating the electric field along a radial line yields the voltage between the cylinders. Delta V will be equals to lambda over 2 pi epsilon naught times the integral going from A to B of dr over R, which will be equals to lambda over 2 pi epsilon naught times the integral of dr over R is the natural log of R, and which when we put the limits gives us logarithm of B over A. Following from the definition of capacitance, C will be equals to Q over delta V, where Q is equals to lambda times L and lambda is the linear charge density. We get C is equals to lambda times L divided by lambda over 2 pi epsilon naught times natural log of B over A. And that finally gives us 2 pi epsilon naught times L divided by the natural log of B over A. This is the capacitance of a cylindrical capacitor. Spherical capacitor. The capacitance of spherical capacitor can be determined by calculating the voltage difference between them for a given charge on each. The electric field outside a charged conducting sphere is found by applying Gauss's law to it. The electric field is equals to Q over 4 pi epsilon naught times R squared. Integrating the electric field along a radial line yields the voltage between the spheres. So delta V will be equals to Q over 4 pi epsilon naught times the integral dr over R squared with limits going from A to B. and which when simplified gives us q over 4 pi epsilon naught times 1 over a minus 1 over b. Following from the definition of capacitance, C will be equals to Q over delta V, which is equals to Q divided by replacing the value of delta V with Q over 4 pi epsilon naught times 1 over A minus 1 over B, and when simplified we get 4 pi epsilon naught times AV over B minus A. So this is the capacitance of a spherical capacitor. Isolated sphere. Capacitance exists in an isolated charged conducting sphere. Although application for such a capacitor may not be obvious, it does demonstrate that a charged sphere has stored some energy as a result of being charged. Using the capacitance expression for concentric spheres, we get C is equals to 4 pi epsilon naught times AB over B minus A. If B is large enough, as B approaches infinity, we have C will be equals to the limit of B going to infinity of 4 pi epsilon naught times AB over B minus A. And that gives us limit B going to infinity of 4 pi epsilon naught times A over 1 minus A over B, which is equals to 4 pi epsilon naught times A.